Hello everybody and welcome to the presentation of our work live in the Express Lane. I'm Patrick Jahnke and this work was in cooperation with Vincent Riesop, Pierre-Louis, Pavel Chuprikov and Patrick Eugster. In the last decade, a tremendous increase in internet connectivity and the need for more computational performance changed the way we conceive applications. Today, most new applications are designed as distributed and in particular cloud-native applications. Most distributed system designs treat the underlying infrastructure as a generic communication system. One of the main issues with this abstraction is the long-standing problem of interference of concurrent interactions and thus unpredictable latency of commodity networks and hosts. Many applications and components have been designed to cope with unpredictability of the infrastructure by making weak synchrony assumptions to guarantee a safe execution of their protocol. They rely on upper bounds for the latency of their interactions to ensure liveness by defining timeouts and as thus benefit strongly from interactions with low latency and bounded jitter. Therefore, one of the main challenges in terms of performance of a distributed system is to mitigate interference in a data center commodity system. To do so, it is important to get a better understanding and awareness of timely sensitive interactions and tighten upper processing and communication bounds for practical purposes. This would solve the long-standing problem of the unpredictability of transmission and processing times for individual packet and, in particular, asynchronous behavior of commodity network and hosts, which is the foundation to increase the performance of distributed system coordination tasks like failure detection and consensus, which are widespread in practice. Current-related work can be categorized in two areas. The first one is focusing on low latency. The works in this area decrease the latency for all types of traffic, but considering in their evaluation usually the 99th percentile. Furthermore, they are pure transmission times and throughput considered, but no processing times. The other category is focusing on network support for specific tasks or for a specific service. They have usually specialized hardware requirements, but do not consider end hosts and its processing times. Overall, the common understanding is that communication links are reliable but asynchronous. The idea behind the Express Lane, or X-Lane for short, is an interference-free environment for selected interactions with ultra-low latency and bounded jitter for communication and processing. The remaining interactions follow common design principles. Even if in this work we are focusing on coordination traffic of distributed systems and show the benefits for asynchronous algorithm of bounded communication and processing latency, we designed X-Lane in a generic fashion to support different types of protocols, and it should be executable on commodity and new generation of data center hardware. To realize an interference-free environment, we isolate X-Lane with its services from the regular system, since processes of the regular system have to deal with shared processor time. This resource sharing introduced unpredictable jitter for those processes, while critical interactions need an upper bound for certain tasks. In the network, X-Lane prioritizes its packets to prevent packet loss due to buffer overflow. To communicate from the regular system to X-Lane and vice versa, X-Lane provides two sets of queues called bridges. Here, visualized as cuboid, to establish the interface between processes in X-Lane and the regular system. The express to regular bridge in green grants write access to X-Lane, which is the green parallelogram, and read access to the regular system, here in blue. Inversely, for the regular to X-Lane bridge, visualized as a blue cuboid. Bridges are addressable using direct memory access, but are placed at different locations depending on endorsed hardware available. We see this in the next slides. What we see here is a very common example of the workflow for a communication between two applications. In this case, application 1 running at core A.X on host A, and the corresponding application 1 running on core B.Y on host B. So let's go through all sources of jitter that might have effects on the latency. For an application that shares resources with other applications, the operating system has to handle the sharing with the scheduler. Also, an idle state or frequency scaling of a core introduce execution delays for the application. Once the application has the execution handler from the scheduler, the application can start to process data and creating a packet. Then it has to go through the kernel, more or less extensive. I come to this point in a minute. But in this case, the packet goes through the protocol stack and the NAPI driver and the device-specific driver. All processing steps can be interrupted by many different things like interrupt request, tick timer, read copy update watchdog, and non-maskable interrupts and system modes interrupts. Then we also have to consider that the core and the NIC are at the same NUMA node. Otherwise, we would introduce QPI traffic. Once the packet is transferred to the NIC has its own buffer, which might be occupied, and therefore queuing latency can be introduced. On the switch or switches, depending on the number of hops, queuing latency can be also introduced. And since we have a very limited number of dedicated per port memory and also limited shared memory over all ports, the packet might be dropped if the queues are already full. On the receiving side, we have basically the same steps. The only difference is that usually you have to raise an interrupt that the host system copies the packet from the NIC to the host. As mentioned before, with techniques like DPDK, you are able to prevent certain steps in the kernel, especially at the protocol layer. With X-Lane on commodity hardware, we cut one core out of the rest of the system and disable all possible sources of jitter. The core is running on max frequency all time. And while the IRQ can be handled by other cores, the tick timer has to be blocked during the X-Lane execution. The other effects are disabled. X-Lane is implemented as a kernel module. Therefore, we designed bridges between asynchronous user space or the rest of the system and X-Lane kernel module. The kernel module interacts with the NIC driver directly. The X-Lane core obviously is running on the same NUMA node as the NIC. On the NIC, we created a dedicated buffer for X-Lane. Same on the switches, where we use the strict priority technique with a dedicated X-Lane queue, which has the highest priority. On the receiving side, we also defined a dedicated receiving buffer for X-Lane on the NIC. After receiving a packet, the NIC raises an interrupt on the end host. To estimate the latency, we created a traffic engineering optimization algorithm that also takes care that the queues are not oversubscribed. X-Lane has also a control mechanism to share the resources and timings through the system. We also implement X-Lane on new NIC generations, so-called smart NICs, more concretely on Metronome Smart NICs NFP 4000. With this design, we offload the X-Lane kernel module down to the NIC. Therefore, other system modifications are not needed anymore. But we're still using the bridges, but now between the NIC and the main CPU, and also using the control mechanisms explained before. We now present a heartbeat failure detector, which we implemented with X-Lane. We run the experiments over 21 days, but the plots here are just cutouts with the highest jitter points. All graphs are visualized in the same way, with the number of packets on the x-axis and the latency on the y-axis. With X-Lane on commodity hardware, we don't really see outliers anymore, and the jitter is around 650 nanoseconds. The jitter is mostly coming from the PCIe bus, because if we run X-Lane on the Smart NIC, we see even more stable jitter. We compared different X-Lane implementations with DPDK, which is, as discussed before, the foundation for a lot of related work in the area of traffic optimization, and QJump. As you can see, DPDK and QJump have outliers in double-digit millisecond range. So please consider the different scales for the latency on the y-axis. We see here the latency on the y-axis and the different percentiles on the x-axis. Please also consider here the log scale on the y-axis. Here, we also visualized X-Lane 0, which is the same code as X-Lane, but without a dedicated core on end hosts. If we now consider the distribution of the different approaches over 21 days, we see that X-Lane was over the whole experiment very stable, while DPDK and QJump is having multiple jumps, which makes it hard to define upper bounds on latency. This is probably also the reason why other approaches in this field consider only the 99th percentile, even if they talk about bounded latency. Now, we also implemented the Raft protocol on X-Lane called X-Raft. We compared it with etcd and Redis, which doesn't use a strong consistency state replication mechanism. And we were able, by changing 20 lines of code of Redis, using X-Raft below. What we see at the plot is the average latency for writing on the y-axis and distributing the value over increasing number of processes on the x-axis to show scalability. On the right-hand side, we see the average throughput in megabytes per second on the y-axis and also the increasing number of processes on the x-axis. We see that X-Raft performs best and even better than replication mechanisms without strong consistency. To conclude, X-Lane provides an interference-free environment for low latency and jitter for coordination traffic. X-Lane is isolated from the regular system, but is able to communicate to the regular system over bridges. It has a generic system design to accelerate different types of interactions and is executable on commodity software and hardware and also on SmartNICs. With this, I'm finished with the presentation of our works on X-Lane, and thank you for your attention. And now I'm happy to answer your question.